Now we will move to the second part of the induction of torque in DC machines, in which the first part we already talk about the induced voltage, okay, in DC machines, and how we can compute that, which is through calculation of machine constant and the total flux in the machine, as well as the speed. Okay, now when we talk about torque, okay, so torque is basically the moment or the forces that are making the object rotates. Okay, so in this case, if that forces are or happens or created away at some point away from some center of rotation, then the object will rotate. Okay, so if we take a look at this view of a coil that are located inside or in between of a permanent magnets, in which obviously you will get flux lines between say from north to south. Okay, so I'm just going to select this. Okay, so from north to south, okay, from north to south, which is like this. Okay, all right, so when you close this switch, okay, so when you close the switch, obviously you will have a straight line going from here to here, and you will close the circuit. Okay, and the current will flow from positive side of the battery inside through the coil like this. Okay, so if I probably change the color a bit, so and okay, like this, and then the current will actually flow like this, okay, through the coil, all right, and back, all right. So we can see that the current actually flows when the brushes here touches the commutator, all right. So when the brush touch the commutator, then the current goes through the coil and out from that coil into the other end of another commutator to complete the circuit. Now we know that from chapter 1 that we have gone through this before this, that the force actually induced when we have current flow inside a conductor, in which the conductor is already in a magnetic field. So if we look at this diagram, okay, this small diagram here, we can see that the current is for this side. Okay, the current is, you have a dot, so that means current is coming out from the page. All right, so we know that the induced forces is the current dot with the length cross product with B. Right, so since the length doesn't have direction, we're going to follow the direction of the current. So the current is actually going out. Okay, so if you use the right hand rule for a cross product, so you use your thumb, you have your thumb going up like this, okay, and then you have your middle finger going out of you, and then you not your pointing finger, and then you have middle finger going perpendicular to that. So this is the result of the cross product. So the thumb would be the length, okay, the pointing finger should be the B direction. Okay, so if we take a look at this, we know that the current is going out, so your thumb should be pointing towards you. Okay, and then your B is going to the right, right? Okay, so basically if the B going to the right and the thumb is pointing towards you, then the middle finger will point upwards. Okay, that's why you get F, something like this. Okay, so if you look into the YouTube videos that I've put in the previous pages, the author actually talks about a Fleming left hand rule. Okay, you can use that as well, but it's going to be the same results. Only for each finger, it's a different connotation, or it's a different variables. Okay, I like to use the right hand because if you have a cross product, no matter what kind of arrangement or what kind of equation it is, the what do you call, the arrangement of what variable goes first and second is the same, as long as you know what cross what, and then the thumb is always going to be the first variable, the pointing finger would be the second variable, and the result is your middle finger. Okay, so I hope that clears out. You can use Fleming left hand rule if you want. You just have to memorize what goes into what finger. Okay, all right. Now we know that you have forces on this side upwards. Okay, and then you have forces on the other side downwards, because the current actually now, instead of going out to your screen, it's going in. Okay, so if you have forces like this, and the center of rotation is here, which is you have forces from a distance, forces at the distance from the center of rotation, the whole thing will actually rotate, right? So, oh, I'm sorry. I apologize about this. What do you call this? The equation is flipped. Okay, anyhow, the forces that are created will actually depends on the location of the conductor inside the machine. I already explained about this before, that the conductor BC, BC, and AD obviously will not produce any forces, because it is in the direction of the magnetic field. Okay, so the current that actually flow throughout this, for example, BC, okay, if the current actually flows from okay, so if the current actually flows through from B to C, for example, okay, in this case, if the current flows from B to C, B is, for example, in this direction, and current flows in this direction. So for BC, okay, the conductor BC here, because it's parallel to the it's parallel to the direction of the magnetic field, then obviously current, the direction of the current will have no angular difference between I and B. Okay, so since cross product is LB sine theta, so if the angular difference is 0, then obviously this term is 0. Okay, so that's why you will be multiplying LB with 0, so therefore BC will have 0 results. Okay, so that's why you have forces only on this side, okay, and this side. All right, so the amount of forces that will be induced is ILB. Okay, so remember, as long as the conductor is under the face of the pole, you will always have this maximum value, right? So now the torque is actually calculated by the what you call, the distance between, or the radius of your coil, right, from the center of rotation. Okay, because the torque will actually, or the moment will actually be computed when you have a force at a distance from your center of rotation. So that's why you have R here. So the torque will be R times F sine theta. Okay, so therefore, because your what you call, the force itself that we created will always be tangent to the direction of motion. Okay, so therefore sine there, okay, will be always 90 degrees. So you will have the value is RF or RILB. Okay, so if you put ILB inside F, then you will have that term. So if we add up all of that together, you will have 2RILB as a total induced torque. So under the pole faces, you will have this value. So beyond the pole edges, obviously, there is no, the magnetic field is no more perpendicular to your conductor, then you will have 0. So therefore, we will also use the pole surface area as a representation to replace the term R here. Okay, so we will have, remember that AP, okay, so AP is pi RL. All right, so if we replace R with AP over pi L, and we substitute this term inside this, what you will have is this one. Okay, 2 over pi times AP. AP is a pole surface area. Okay, so surface area under this pole. So you will have the induced torque equal to that equation. Okay, and we know that the pole surface area times the B will be the total number of flux. Okay, so now we see that the induced torque is actually 2 per pi times flux times current. And if we look at this, now we know that the induced torque actually refers to the value of the machine constant. Okay, in this case, because only single coil, you get 2 over pi. And we've seen before that if you have multiple coils with multiple loops arrangement, and you have the way the different ways of either progressive or retrogressive connection from your coil to your commutator, you will have different K. Okay, so but what is the most important is that you have K and phi and I. So the induced torque will depend on the machine constant, the total flux inside the machine, as well as the current that are supplied into the rotor. Okay, right? So in real DC machines, we will look at what do you call the factor that will be affecting the induced torque inside the real DC machines is the motor constant K, the armature current or the current that goes into the rotor, as well as the flux inside the machines.